Hello, how are you? I hope that everything is going well. My name is Tainan and today we are talking about modeling and simulation, so let's go. Why are we studying that? Well, this is the general architecture of our software. We are in research phase yet, but here we can see that we have in the left part user stories. Why? We want to, the Who Captain software, the main goal of the software is to allow any people in the world to be able to create technology, edge technology. And for that, we believe that we have to simplify, so to move software development to higher levels, to abstraction levels that are not code itself. For that, we are building a platform that came from natural language, and then to structured user stories, then high-level models of representation, the static model and the dynamic model, and probably the static model as UML classes, and the dynamic model as machine state chart diagrams. And then from these high-level models, we merge them to form the platform-independent model, a model that, as the name says, is not don't have dependencies to determinate technologies. And from this higher-level model, then we generate PSM, platform-specific models. So these are high-level models, but they have data that is related specifically to the technology, like for UI. They could have data specific to React or Flutter or whatever. For the database, like MySQL, for Oracle database, anyway. And for the selected output programming language, for example, Python, Java, PHP, JavaScript. And from these PSMs, then each of these PSM then generate the final artifact, like UI code, database code, and the selected output programming language code. So from user stories to generated artifacts. But in this model, I saw that first we have to have tests, and at the model level tests. Because when we generate, we want to test and verify our model before generating its outputs. So even before the PSMs, and certainly before the final artifacts. Yeah, we have content on the subject of tests themselves, but I think that today even with TDD, test-driven development, we look to tests in a way that's very attached to software development, to the code. So we create a code and then we create tests for the code, or the most times using the same language code for doing that. And I think that we have to go in the way that first, we generate and recreate the scenario as a whole, like what's the problem here? So the domain is, I don't know, CRM. So we create the customers, we create the sense of time of this domain, and then we create the purchases and all of these things before we go into the code. Because this way, when we go to the code, all the scenarios are already created, and then we can the developer can solve those problems in a way that's very intuitive. All the scenarios probably are already created, and if not, we can change the scenario instead of changing the code. And the task of creating the software, in my view, if we are able to do this change on software development, becomes more fun, like we are solving a game, right? Because the scenario is created, we have to solve the challenges that are already occurring, on that scenario like a game. And for that reason, I studied modeling and simulations for the last weeks, and let's look into that. What is modeling and simulation? Modeling is one of the ways to solve problems that appear in the real world. In many cases, we cannot afford finding the right solutions by experimenting with real objects, so we build a model of a real system. We are using this book as a source, but here we have an example. Like I said some videos ago, here we have the real world, and here we have maps. The maps are models of the real world. So the idea is looking into the real world, bringing the important characteristics of the real world scenario into some kind of model. We can see the types of models here. Changing or testing or trying this model, right? Like if it is a spreadsheet, changing the parameters and the variables, looking for better solutions, and then applying that solutions on the real world. So we abstract the real world, we apply changes to that model, and then we apply those changes, the good ones, on the real world. Using less money, because, for example, if we are modeling cars to simulate crashes and a lot of things, this would cost a lot of money in the real world, and doing it faster in the models, using models. The other types of models: mental models, physical models, formulas on a sheet of paper, boxes and arrows. These are very similar to state charts and computer simulation models. Here we are going to see the three main methods of modeling and simulation. The first one, system dynamics. The second one, discrete event modeling, and the third one, agent-based modeling. You can see stocks, flows, and feedbacks. They are related to system dynamics. Entities, resource, and operations. They see the world. They model the world similar to processes. So the world is a sequence of processes. And the agent-based modeling, they use agents and behavior, rules, interaction between the agents. So each one of them are agents. The definitions: system dynamics is a method of studying dynamic systems. The idea is to use the laws of physics to describe and investigate the dynamics of economic and social systems. What I can say about system dynamics, it uses a lot of math, and the modeler has to know a lot of the system as a whole, because he has to define the system using math, and for that the modeler have to know how the majority or all the actors of the system behave to build a good model, right? So remember, a lot of math. Discrete event modeling. The modeler considers the system being modeled as a process. For example, a sequence of operations being performed across entities. So here, the system is modeled using processes. So each block of the system, of the model, is a process, and we can say, if we run the simulation, how each process is behaving, its own statistics, and the queues. For example, for a bank, we can model the ATM machines queues. So we have the door of the bank, the queue, the number of ATM machines we have, the support people, so the attendants, and see how the bank is modeled, and each one of the actors modeled as process are behaving. And the last one, agent-based modeling. You may not know how the system as a whole behaves, but you may have some insight into how the objects behave. Therefore, you can start building the model by identifying those objects that are called agents and defining their behaviors. So here we can see that ads is one of the agents, staff is other one, and the consumers are agents as well. In this case, we model the system as having different agents. So, for example, consumers, products, ads, and how these different agents communicate with each other, like how the ads impact the consumers to make purchase of products, for example. This one, from the three, I think that's the one that it is more related to what we are studying at this channel at Hook Captain. And if we have sufficient memory and computer resources, is the easier one, in my point of view, to create. So it comes, it goes in the way that we are looking to. Some details of agent-based modeling. They use object-based architecture. So each one of these agents, we can see them as objects, or if we want to relate it to the UML classes, we can see the agents as the main classes of a domain, and the objects as the instance of the classes, right? It has a time model, asynchronous or synchronous steps or clock ticks, like in the consumers and products and ads. We have time, so we have the time 1, the step 2, the step 3, and we have the state machines. So each clock tick or each step ahead, we can see the simulation going on. We have space. We can use, or we can choose not to use them, but we have space, 2D or 3D, and mobility. We have networks and links between agents. This is very similar to the concept of relationships and associations that we have on UML. We have communication between agents and between agents and the environment. So the ads object, the ads agent can communicate to the consumer agent, right? So and the opposite is true as well. And both can communicate to the world. So the environment agent, that's the one that the other agents are inside. So for example, if we want to model families and families trees, we have females and males, they marry each other and they create children. This step of a baby born, a child being created into our simulation could be, for example, a request communication between the female agent to the environment to create a child in that environment. So create a child object, right? As I said, dynamic creation and destruction of agents. For example, in this model I said, the death of one of the objects. Statistics collection on agent populations. So as the simulation is going forward, we can see how it's behaving. So here we have some examples of agents. And here we come to the real world, which software are implementing simulation and modeling. AnyLogic is the one that is related to the book that I use it as a source. So it's the one that I studied. But they have some competitors. MATLAB and Simulink is one of the leaders of the market. And we have some others, Arena, SimScale, Simulate, and SolidWorks. Here, I want to explain in general, in short, how AnyLogic works. They have, each one of these steps is one agent, right? So as I said, the environment is an agent, so you can model the main things in this main environment, this main agent. Here we have some meta objects. What are them? They are objects that are useful to the engine itself, not to the application domain. So for example, source, some objects. Here we have delay, and here we have move to, for example. Why would you use each of them? Source is useful to include, to create some objects into the simulation. Delay, you could use, for example, this example is a fabric, and here we have some machines of the fabric, for example. We could use delay to simulate the work of that machine. So the machine receives the pallet and then make its work in the product, in the content of the pallet before the product is done, for example. And we could use delay to simulate that behavior. And the move to component, meta component, is used, for example, to move this truck from here to here, where it could pick the pallet to bring to the machine, for example. So here in these steps, you can create these flows, these processes, these to create the behavior of the simulation of the agent, right? Here you have you can add the image that is used as the background of the simulation itself. So, and you can annotate the image with other meta objects. So, for example, this is the what's the name? Source palettes. Source palettes meta object that is used to make the trucks move to this part of the image, right? To simulate then picking the pallets. So in the same tab, you can add the background image of the 2D simulation and annotate the image with some useful components, meta components for the simulation engine. And here you can see there is a camera meta object that is placed here, right? And here we have the same idea. Okay, one thing that I didn't say, here we have the simulation when in runtime, right? So here we have the window that we create the behavior, we build the behavior of the agents and the simulation, and here we have a play button here, compile and play, and here we have the simulation in runtime. So here, if you use the software, the engine, you can see the trucks coming here and picking the pallets and moving to the machines, and the things going smoothly in runtime. And they have some content, so they have sprites that you can use to illustrate the agents. That's very, very interesting. And here we have the same runtime view of a most complex simulation, like here in the 2D view of a hospital simulation, trauma center simulation, and here the 3D view. You can see the doctors and nurses and things going on the trauma center, right? So that's all for now. Thank you. In this video, we saw what is modeling and simulation. We saw the three main methods. We saw the agent-based modeling in detail, and then we saw some software that are implementing modeling and simulation in the real world, especially AnyLogic. That's the one that we choose to understand better, right? I hope you liked the video. Please like the video and subscribe to our channel, and we come back soon. See ya.